Welcome back. Lecture 17.3, where we're going to continue our discussion of entropy. Okay, so last time we defined a quantity around a closed loop, dq r over t, which was 0, which we said satisfied our conditions for the entropy S. That is, around a loop, for the full process, the coming back to the same spot, it was the entropy was 0. But now, does this yet imply that the quantity is independent of path? So imagine two states, A and B. Is the integral from A to B of dq r of t equal to 0, is it independent of path? That is, if we move from A to B, either, let's say, along an isotherm or along some part of an adiabat with either an isochore or isobar, right? Combining things, was this function independent of path? Well, as long as it's reversible, right? For a reversible path, let's imagine. Okay. So for reversible path, let's say reversible processes. Let's imagine on a PV diagram going from A to B along some path, let's label it 1, and some path, label it 2. Does it matter? Does this quantity matter how we got there? Okay, so what we want to do is we want to show that. What we want to show is that the integral from A to B of dq t along path 1 is equal to the integral from A to B dq t along path 2. Okay? So if path independent, we would need to show this. Well, we've already said, though, along the loop it must be 0, right? So if we had A to B along path 1, but then we subtract path 2, it would have to equal 0. Well, sorry, let me write that. Let's say moving from B to A. Along path 2. But going in one direction, as long as they're reversible, then this is the same as what I wrote before, which was I can flip that, right? So for a reversible process, I can always go from, instead of B to A to B, and I'm just going to get the minus sign. Which we can rewrite as so. In fact, this quantity is path independent, right? So what do we call something that only depends on the state you're in, but not how you get there? This is called a state function, right? So the entropy, let's say, so that the integral along a path is a state function. Okay, why did I avoid calling that the entropy? Well, because we haven't fully defined the entropy. We've only said that the entropy can change. So imagine that the entropy at some state A, like this state, well, I had to imagine getting there along a path. So I had to have some state zero to get there. So entropy is defined really as a change from one state to another. And we need some other universal state to define absolute entropy. Right? To define the entropy at this state, I'm really saying that this has to be, the entropy at state A minus the entropy at some universal zero state, right? And we haven't defined what that is. So instead, what we've been defining really is the change in entropy. And the change in entropy is much easier to think about, right? So the change in entropy, you would say, is the difference between some state B and some state A, right? Which would be the integral from A to B of dq t. Now that's consistent with this, right? If we could say, well, that's the same as integrating from A to some arbitrary state plus from that arbitrary state to B. Right? So this would be S of A plus and then I could have this one. Oh yeah, sorry. This one I need to flip, so this would be minus 0 to A dq over t plus 0 to B dq over t, which is minus SA plus SB. So the change in entropy from two states is easy to define. To define an absolute entropy, we really need some other offset, right? So it's still fine to have this, but we really need to know what the entropy of this zero state is. And a little bit later, we're going to use the third law of thermodynamics to help us set that, okay? Now, a couple last points about the entropy. Since the entropy is a state function, since S is a state function, that means that it's our ds is an exact differential. So that's quite interesting because dq was an inexact differential, but we made the entropy an exact differential by taking dq over T. So dividing by the temperature makes the entropy independent of state, or a state function, and an exact differential. Okay, so what are the units? Well, they must be the units of energy, Q, which is joules per Kelvin. But we can also define a molar entropy, which will be useful sometimes. So little s, which will be big S over N, and the units will be joules per mole. Okay? And what's called the specific entropy, which is big S over M. And that's joules per kilogram Kelvin. Now, everything we've done so far about entropy is for reversible processes. And next time in lecture 18, we will talk about entropy for irreversible processes.